We have said that specific solutions of an ODE are called trajectories. Sometimes we want to compute them exactly. Sometimes knowing them approximately is good enough. When we want to compute them exactly, we need to use some of the analytical tools we have developed until now. So in particular, there is one method to solve it that is only for autonomous systems that relies on rewriting dx dt equals f of xy, dy dt equals g of xy, so a 2D system, autonomous and nonlinear. We rewrite this as the fraction between dy dt and dx dt, that is dy over dx, as the fraction between g and f. So now we move from an autonomous system in which x is a function of time and y is a function of time to a situation in which y, we're kind of interpreting it as a function of x. Not really though, because we're interested in trajectories that are not necessarily a function of x. So now in this situation, the intuition is lacking a little bit, but what we want to find is solutions of the form a function of x and y equals to a constant. So we're changing our structure from having a function x depending on t and a function y depending on t to having the ratio between dx and dy. And we study that ratio to find a function function h depending on x and y, and the contour plot of h, that is the slices given by h equal to a given constant, gives us some information about the shape of the solution. As you have to be a bit careful because we have taken the assumption that y can be written as a function of x. So if we solve explicitly dy over dx equals g over f, we are assuming that y is a function of x. That is not necessarily the case. So you have to be a bit careful about that. You also have to be a bit careful about the fact that in this new system, dy over dx equals g over f, we have lost information about time. So we're able to retrace the shapes of our trajectories. We're not able to understand how fast or how slow or in which direction we're following these trajectories. To understand that, you have to go back to the initial ODE system. For example, we can consider x prime equals y, y prime equals x. It's a linear ODE system, so we can actually rewrite it as the vector xy prime equals the matrix 0, 1, 1, 0 multiplied by the vector xy, and we know how to solve that. But we can also solve it through the method we just described. So we're going to write dy over dx equals x over y. And in this case, it is separable, so we can write y dy equals x dx. And we can solve this, and we find that the function that we need to solve in order to determine the trajectories is h of x and y is y squared minus x squared. So we want to set x squared, y squared minus x squared equals to a given constant and draw the lines determined by that. If you're only drawing the lines from h, so the height of h, we don't know the direction of motion. So we have to go back to x prime equal y, y prime equal x to put the arrows in this picture. Let's go for a second example. We have dx dt is equal to 3y minus 7, and dy dt is x squared minus 4. So dy over dx becomes x squared minus 4 divided 3y minus 7. That we can write, we can again separate, we can again doing the separation of variables and the integration, and we retrieve that the trajectories of this ODE system need to satisfy 3/2 y squared minus 7y plus x to the third divided by 3 minus 4x equal to c. While this is an information about the trajectories of this system, it is not something very easy to plot. So we want to write the contour plot of this H. And by hand, that is close to impossible. So I have written a very simple MATLAB code that uses the contour plot functionality of MATLAB to do exactly that. This is a very brief code, as you can see, is only 2 lines long. I wrote out the function we just found that depends on x and y. And I use this f contour that is a built-in function in MATLAB. It requires a special package that takes f, the bounds on which we want to write, and possibly a list of levels, that is of constants, to plot that. And if we run this, we retrieve information about how the shape of our trajectories is. It might not be super clear. I'm going to post the MATLAB code in the course, but each one of these lines that you're seeing is the shape of one of the trajectories. In order to understand in which direction we have to follow it, we have to go back to the ODE, because it doesn't give us this information. But it gives us some information that around a critical point we have some kind of circular behavior. Then there is a separatrix that has a form of an alpha-like, and outside of that we have some behavior that just goes around the alpha. Directionality is not given.